Okay, so for this assignment, we had to find the muzzle velocity of a weapon, and then using that muzzle velocity, we then had to find the maximum distance of said weapon. That's it.
The materials used in this lab
Experiment.
were a Nerf gun, a piece of chalk, and a meter stick. For the first procedure, we had the Nerf gun at 0 degrees and a meter above ground, and we averaged them to find the muzzle velocity. And for the second procedure, we had the Nerf gun at a 45-degree angle to find the max distance.
Okay, so to calculate the muzzle velocity, first we need to start with a little graph, a little table to show our x and y values. Okay, so we don't know our original velocity for x, so we leave that blank, and we assume that for y, it's 0 meters per second. For our x, our initial position is 0 meters, at least that's what we're assuming, and for y, it's 1 meter since we started from the meter stick up. For our final position in the x, we averaged the numbers together to get 158 meters. And for the y, it ends in the ground, therefore ends at 0 meters. The acceleration for x, we are assuming that it's 0 meters per second squared, and for y, it's negative 9.81 meters per second squared, because that's gravity. We don't know our time, so that is what we're solving for right now. So we start with the equation y equals y naught plus v naught y t plus 1/2 at squared. And we plug in our known values, which would give us 0 equals 1 plus 0t minus 4.905 t squared. So that equals nothing, so then you have 0 equals 1 minus 4.905 t squared. You move the 1, you get negative 1 equals negative 4.905 t squared. You divide by negative 4.905. T squared equals 0.20387. So if you square root both sides, that will give you t equals 0.4515 seconds. So once you have that, you can calculate your initial velocity. You plug it in here because both the time is the same for both sides, and then we can use this to solve for our initial velocity for x. So x equals x naught plus v naught t plus 1/2 at squared. Since our acceleration is 0, we can cross that out, and we plug in the values that we know, which are 0 equals, nope. Okay. We can plug in our values that are 8.58 equals 0 plus v naught times 0.4515. So 8.58 equals 0.4515 v naught. So if you divide both sides by 0.4515, you get v naught equals 19.067 meters per second. 0.61 meters, but we're going to solve for our actual maximum distance considering perfect conditions. So for our initial x position, we're assuming that it's 0 meters, and we shot the gun from the ground, so we can assume that y is also 0 meters. So for our final x position, we don't know what it is, so we'll just put that as a variable. And our final y position is 0 because it ended on the ground. Our initial velocity for x was the magnitude of the initial velocity, which is 19.067, which we got from our last problem, times the cosine of 45 degrees, which will give us 13.48 meters per second, which is our velocity, our initial velocity for the x. For the y, it's 19.067 times the sine of 45, which gives us the same number, 13.48 meters per second. 13.48 meters per second. So for our time, we don't know what that is, but we do know that our acceleration for x is 0 meters per second squared, and for y it's negative 9.81 meters per second squared. So now we need to solve for time in the y so that we can fill it in for it to solve for our final maximum position. So we start with y equals y naught plus v naught t plus 1/2 at squared. So since we know that our final y position is 0, that our initial y position is also 0, that our initial velocity is 13.482, and we are solving for our time, and we know that gravity is negative 9.81 meters per second squared, and that divided by 2 is negative 4.905 t squared. So once you do that, you do 0 equals 13.482 t minus 4.905 t squared. After that, you move the 13 to the other side, 482 t. Move it to this side. So you have negative 13.482 t equals negative 4.905 t squared. So now you divide by t to get rid of the quadratic on that side. So you have negative 13.482 equals negative 4.905 t. You divide by negative 4.905 on both sides to get t equal to 2.749 seconds. Once we know that, we can plug it into our table. Okay, and once we have our time, we can actually solve for our maximum distance. So we use the equation x equals x naught plus v naught t plus 1/2 at squared. We know that we don't know our final x position, but we do know that our initial x position is 0, and that our initial velocity is 13.482, that our time is 2.749, and since the acceleration is 0, then we can just chop that off because 0 times anything is 0. So then when you solve for that, x is equal to 13.482 times 2.749, and when you put that in the calculator, it gives you 37.062 meters, which is our maximum distance if conditions were perfect.
So when we went outside to calculate the muzzle velocity, we got an average, out of these numbers, we got an average distance of 8.58. And then after we plugged that into the equations, we got a muzzle velocity of 19.067. And afterwards, when we did the second part of the lab, where we shot it at a 45-degree angle, or we tried to at least, we got the max distance of 25.61. But after doing the calculations, the actual max distance should have been 37.062.
Our assignments were to find the muzzle velocity of a Nerf gun and then the maximum distance that the Nerf gun can fire. To do this, we used S equals S naught plus V naught T plus 1/2 AT squared to find the time and the muzzle velocity. To do this, we used S equals S naught plus V naught T plus 1/2 AT squared to find the time and the initial velocity. Then we went outside and we shot our Nerf gun at a 45-degree angle, wasn't exactly 45 degrees, to find the maximum distance, and then we calculated it and compared the two answers.